Hey everyone, welcome. This is the A16Z YouTube channel. My name is Ali Yahya. I'm a partner on the A16Z Crypto Fund. And I'm here today with Ben Fisch, who is a student, a PhD student under Dan Bonnet at Stanford University, and has done a lot of very interesting work in the area of blockchains and cryptocurrencies, including some work on proofs of replication, as well as more recently, accumulators. And today we'll spend a lot of the conversation talking on proofs of replication and sort of their implications, and in particular, what they mean for decentralized storage. So Ben, thank you for coming along.
It's great to be here, Ali. Thank you for the introduction.
Of course. So what is the problem of decentralized storage?
Well, decentralized storage is about taking all the storage we have today, the massive amounts of storage we have today, sitting in centralized cloud centers, right, like Amazon or Google, and distributing it across the internet of internet-connected devices. And you know, there could be many different benefits that one could talk about there, but the problem of how you actually go about doing that and checking that if you take a file and ask some random distributed nodes across the internet to participate in storing the file or even just pieces of the file, say people with extra space on their phone who are just contributing to the collective storage, how do you verify that those files are actually there and still being stored and are retrievable?
Yeah, it is a very interesting problem space because we can take for granted almost that there is an enormous amount of unused latent storage space inside of computers that are maybe mobile phones, that are laptops, that are desktop computers, or maybe blades inside of servers and data centers that's just completely unutilized. Not even underutilized, but fully unutilized.
Right now.
Absolutely, yeah. Like,
how much unused storage do you have on your phone?
Let me just. So I currently have 70 gigabytes of unused storage on my phone. And I think it's probably a safe assumption. You could say on average, maybe half of the hard drive of any one particular computer is likely to be unutilized.
You could store the entire Lord of the Rings trilogy on your phone at times 10 and contribute to a decentralized, file storage network.
So the problem then of decentralized storage is how do we spring up a marketplace that's able to tap into that unused resource? How do we create a protocol that is neutral, that is open source, that is kind of like another sort of layer to the internet that incentivizes people to put up their unused storage that they have in their computers on this sort of network, such that other people can rent that storage and make use of it in a way that's actually useful.
Absolutely.
And it's controversial too. Is like there's a question is why is it that this problem matters? Like it could be yes, there's an economic argument you wanna get to that storage, but is it really that much cheaper than the kind of storage you can get on Amazon S3? Are the economics make sense?
There's an economic question. There's also a censorship question, right? If you have Amazon in charge of all the storage, then maybe Amazon is not intending to censor individuals, but say a government it's much easier for a government to prevent Amazon from serving files to their country than, a amorphous internet of connected devices that are participating in storing just pieces of the file.
Absolutely.
Yeah.
Yeah, I think that the censorship question is very important. There's like there's a key difference here that if you were to succeed at building a decentralized storage network that is open source and is decentralized, in that the human power over the network is decentralized, and no one human actor or human group controls it, then you end up having some of these additional properties, that it's censorship resistant. You can trust that sort of the rules that make it a platform will stay the same or will stay fair because they're controlled sort of by a body of representative human actors. And so in my mind, I think that like the three things that I think make this problem matter are: one, is what we talked about. It increases the utilization of an unused resource. and there's something that's good about that. There's an economic argument. There's the censorship argument, which is that this could become like the robust storage layer for the internet that is just more fault tolerant and more reliable, more long lasting than the existing model where you have like a single server serving a file, and if that server goes down, the file goes down.
Absolutely.
And then the third being that we talk a lot about kind of the decentralized future of all sorts of applications that can be built on top of blockchains.
Decentralized computation, decentralized accounting systems,
exactly.
Bitcoin, Ethereum.
All of those will require storage, and if that storage were centralized, then the whole point would be lost.
Right.
That would be the weakest link. So you need decentralized storage for those applications to come along.
You can think of a decentralized accounting system, Bitcoin being the first example of such, as a example of a decentralized storage network. It's just that the one file that the entire system has decentralized the storage of is the ledger itself. And so the idea is to have a highly replicated and immutable copy of the state of the financial system, right? And then other networks that move from accounting systems to decentralized computation need the same thing, but for the state of programs being run on the network or the state of contracts between individuals.
That's a very good point.
Right.
Like Bitcoin itself as a decentralized storage network, where the things that's being stored is very specifically the Bitcoin ledger.
Yes.
That tracks basically who owns how much Bitcoin implicitly through its data structure.
Yes.
And then sort of the idea that some other projects out there like Filecoin and Sia and Storj have kind of embarked on is how do you generalize that idea a little bit, and how do you make it so that the storage is general. It can be used for storing anything, not just sort of the ledger that tracks payments inside of the network. So let's talk a little bit about why this is a hard problem. Like why is it difficult to envision this network that no one controls, that creates a marketplace for people to come together and rent their storage to one another? What are the challenges?
Well, usually when we think of what are the challenges, we have to focus on like what's really different from the way things work today. And the way things work today with centralized storage are you know the company that you're giving your data to. The company has a reputation, say Amazon, right? And you put your files in Amazon, and you just trust that Amazon is going to store your data, right? Or Dropbox. And Amazon and Dropbox have a strong incentive to not mess up and continue to store people's data, right? Because if it comes out that Amazon is deleting the data, or if Amazon is not replicating the data enough and therefore has by accident some kind of data fault, then it will severely harm their reputation. So the incentives there come more from a business to consumer perspective.
Yeah, there's the social elements of reputation there,
right,
that kind of keep Amazon and keep all the
Absolutely.
cloud providers in line. Whereas in sort of the crypto world where it's permissionless.
And it's peer-to-peer, it's not business to consumer, where there's a business that has a name that's massively recognized, and now you're talking about peer-to-peer individuals who are, say, contributing just a little bit of extra storage on their phone, and you want to first make it economical for people to earn, a few extra dollars or even cents just on that extra storage that they have on their phone, and not have a really high fixed cost to participation. You don't have to run a business like Amazon for it to make sense to participate. But then from the other end, from a consumer's end who's using this network to store files that they do not want to be lost, there's the question of, well, who's actually storing your files? How do you know they're still storing your files? If there's some random node on the network that might just join and leave, you can't have nodes joining, collecting a few dollars for their storage, and then going away without ever being held accountable for that storage.
Exactly. So it's a permissionless system, and it's peer-to-peer, which means that anyone can participate, anyone anywhere really who has an internet connection and has a computer that's running the protocol can participate.
You don't have to spend millions of dollars on PR to to garner a name like Amazon. You just have a device, you join the network, nobody knows who you are, but yet everybody should be able to have the same trust in you that they have in Amazon.
And so you as a consumer don't have the luxury of relying on like the reputation signal that you normally can rely on when dealing with Amazon.
You shouldn't require the reputation signal.
Yeah, the person you're dealing with is maybe that's someone that's completely unknown. They may be across the world from you, and someone that will forever remain a stranger. And somehow we have to manufacture a different kind of trust.
Yes.
A trust that guarantees to me that my file will be stored.
Right.
And that also guarantees to the person who's storing the file that they'll get paid for the storage. And so then that's where sort of the cryptographic properties of the protocol come in.
It's a trust in protocols, a trust in cryptography, rather than a trust in people.
Yes, exactly.
Traditional business to consumer sort of economics run on a trust in, the incentives of a business, right? Whereas we want in a decentralized storage network to replace trust in individuals with trust in a protocol.
Yeah, Bruce Schneier, the security researcher, has this great framework for trust where he talks about the 4 different mechanisms that our species uses to bootstrap trust.
Okay.
The first 2 are morals and reputation, sort of the very social elements of interactions where you and I, we know each other and we have like direct contact or direct interactions, and so we can come to trust one another through those interactions.
I trust you to store my files.
Exactly. Then there's the institutional trust where you use like sort of companies like Amazon or institutions that have a very long track record and they have a sort of a significant presence as the intermediaries for interactions. And those are the ones who kind of enforce the rules and allow you to trust a complete stranger because they're accountable to this institution.
Yeah.
And the final one is security systems. So you trust that the building is safer just by virtue of it having a padlock or just a lock on the front door. And so what you're saying here is we're shifting trust from institutions, in the case of sort of Amazon and the cloud providers who provide storage, to security systems, cryptography, and sort of incentive structures built into protocols instead, which kind of changes the dynamic because now there are fewer humans involved and therefore this could be more scalable. You can scale trust to a larger number of people. You could imagine this being a truly global decentralized network for storage where everyone can participate because the security is no longer provided by some human entity that has to be involved in all of those interactions.
Right.
So great. So the concerns then are if I put a file on the network and then someone claims to be storing it, they may be lying to me, right? And so how do we? What other kinds of attacks are there? There's I know there's a history of other building blocks in cryptography that are related, like proof of storage and proofs of retrievability, which kind of get at this, but they don't fully solve the problem. I'd love to kind of
let's pick that apart a bit. So if you're just talking about the problem of I put my file into a decentralized storage network and I ask some node whose reputation I have no clue about to store my file, then how can I cryptographically verify that this node is storing my file? And that only requires a proof of retrievability. That's a communication efficient proof, meaning I don't need to ask for the entire file back. Obviously, asking for the entire file back is one way of verifying that they still are storing the file. But it is a proof where they just send me a small tag in response to a challenge that I send them, and I'm able to verify from this interaction that indeed this node is storing my file. That's a proof of retrievability.
Yeah.
Proof that they can retrieve the file. When you start to ask, well, let's say I ask this node to store multiple copies of the file, that again, that's a proof of data replication. But in this setting where I'm interested in just that this node is storing my file, right, and I know what this file is, there are ways of just using proofs of retrievability to verify that this node is storing multiple copies of that file. But then when you start to talk about the economics of an entire decentralized storage network, it seems quite impractical to say, okay, well, you're a user, if you want to store your files in this network, then you have to constantly ping the network to check that it's still being stored there. And that's what you would somewhat need with a standard proof of retrievability. There are ways of outsourcing the verification of a proof of retrievability so that you could, say, ask other nodes to verify that your files are still being stored there on your behalf. And so that's another viable direction, and that's sort of outsourceable proofs of retrievability. But again, then we start to come to the questions of incentives and who is really incentivized to check that other people are storing your files. The economics of that don't necessarily work out, right? You could possibly pay other nodes to check that other nodes are storing your files, but then it starts to look a bit more like Amazon again, say. And so proof of replication, which is the most recent addition to proofs of storage, basically integrates this idea of doing the work of checking that files are being stored with the decentralized work that blockchains brought, right? We look towards something like Bitcoin as an example of a system that incentivizes the collective effort of many different nodes in putting in work into a system. The thing about Bitcoin is that all that work is just sort of computational energy that is, say, somewhat wasted, although it maintains the system in balance. And the current directions for decentralized file storage networks takes that same idea and says, how can we incentivize the massive participation of verifiers and storage nodes and clients who are storing their files in this network, and incentivize the collective work that it takes to check that files are still being stored, verify proofs of storage in a decentralized way, where the nodes that are verifying that files are being stored can earn rewards for that or receive payments, and are agnostic to the actual data that is being stored, so that there's no preference towards one type of data if it's more valuable for a business or not, or another type of data. Anybody can put data into the system. Data is data, and the nodes that are maintaining the network are equally incentivized to make sure that that data is still there.
You're getting at something that's really, I think that is like part of what's so beautiful about the space, is that it, like, so much of the security and so much of what makes everything work is a combination of incentive structures with sort of cryptographic security. And so I think the insight that you're articulating now is that sort of in the world of Bitcoin, the security of the system comes from the computational power of the participants. And the computational power, in a sense, kind of meters the degree of influence that the participants have over the system. But the problem is that that computational power does nothing more than that. And it's otherwise just wasted. It's otherwise just really just empty cycles that are solving sort of puzzles locally and submitting solutions to those puzzles as a way of gaining the ability to influence the state of the Bitcoin ledger. And so the insight that you're describing now is you can combine sort of that incentive structure, which really does get people to do real work, it just so happens to be useless, with sort of this cryptographic building block, such that the work that people do to secure a network now is not just useless computation, but instead is storing files that people actually want to get stored. And so in this same vein, in the same stroke as you secure the ledger for this storage network that tracks payments and tracks transactions and so on, you're also incentivizing people to store real files. And you combine those two things and kind of braid them into a single thing.
That's right.
Which kind of very elegantly solves the problem and provides security and also gets people to store the things that you want them to store.
Right. And to think about things from the perspective of incentives, what Bitcoin is a very interesting example of is a network that is contributing, again, so much energy and collective effort towards one particular goal, which is verifying the Bitcoin blockchain, right? And so it's an example of collective effort being poured in from a decentralized network. And so the goal in current efforts and in my line of research in decentralized storage networks is to turn the problem of verifying storage in the network into some kind of unified goal like Bitcoin, where you get many different nodes in the network to participate in some collective effort towards one common goal, and they're agnostic to the exact effect of that goal. In this case, it's storing files.
Yes.
And so it just seems to be much easier to, at least based on Bitcoin as a case study, right, to offer some kind of reward structure where there's just one task that people need to do, solve proof of work puzzles, and in this case, solve proof of storage puzzles.
Yeah.
And if you get everybody to just participate in solving proof of storage puzzles, and they can earn rewards from doing that, if we can design everything in the background to turn that collective effort into securing the decentralized storage network, that seems to be a really compelling direction towards fixing all these incentive and security issues with decentralized storage networks.
Absolutely. And I think, yeah, I mean, one of the top of mind concerns, at least in the sort of the mainstream media about crypto, is that it's so environmentally wasteful, and that sort of the Bitcoin blockchain alone, and it consumes like more power than like Denmark or something like this.
Right.
And so this is kind of an interesting direction where you can sort of bootstrap security and at the same time also do work that's useful and is not really just wasted.
That's a secondary point that's compelling about this.
Yeah.
Whereas the footprint, you can ask what's the say carbon footprint of a blockchain system or a decentralized system, and you could say that in a decentralized storage network that is based on proof of storage, the footprint is something useful. It's file storage itself.
Absolutely. So I want to hit on the idea of replication. So I think that's kind of an important piece of this. So why is replication important? I mean, I imagine my sense is that you as a consumer would like your file to be stored multiple times in the network, because otherwise, if the one person that you're kind of contracting with for storage happens to disappear or happens to go away, you still have your file sort of stored redundantly with other people at the same time, which kind of gets us why replication is important and is not just really a single sort of proof of storage.
Right. Replication is what gives you fault tolerance and, say, censorship resistance. If there's only one node that's storing your file, then if that node goes down, you could lose your data.
Yeah.
And from another perspective, if there's only one node storing your file, then if anybody could figure out what node that is, then one could launch a denial of service attack against that node, and therefore effectively censor you without being the actual node that's responsible for your data.
Definitely.
So that's why replication is important to a user. Replication might be important to a network for the same reasons, right? So maybe there's not one particular user that cares so much about replication of the entire system, but if we want to maintain the collective state of the entire system, then networks care about fault tolerant data storage as well, and so that's what's important about replication, right? From users' perspective.
Yeah, and so presumably as a user, so I know I want my files to be replicated multiple times. And I want also the knowledge that those kind of replicas are independent from one another, and that like there's some redundancy there that doesn't put all of my files at risk if a single sort of node goes down.
That's right.
And so I can imagine here a potential attack, which I know sort of proofs of replication resolve, is that I could pretend, if I'm an attacker, I could pretend to be many different people. And I could pretend to be storing the file multiple times as if I'm sort of independent people who all have the file independently from one another, but really just have the file once and kind of just sort of route responses to each of my like fake identities to sort of pretend that the file is really stored multiple times. So how do proofs of replication address that problem?
Yeah, well, let me clear up one thing about proof of replication. First, perhaps, the name proof of replication is perhaps somewhat misleading in that I think when people hear proof of replication, they think, oh, well, this is a proof that a file is replicated many times. But really, what proof of replication, the problem of faking that you're storing multiple copies of a file versus storing one copy of the file is the same as proving that you're just using storage in order to store data. Because another way of framing this is to say that, well, I might not actually be storing anything useful at all. I could be storing the digits of pi, which I can just generate on my own, right? Or rather, I could store some sequence that I can generate, like the Fibonacci sequence, right? And that's what I'm actually filling my data with.
Yeah.
And so, just because I can retrieve this unlimited, long piece of data, which is really uninteresting and not useful, then that doesn't mean that I'm actually using all that space.
Sure.
So, on the other hand, proving that you're storing, and that's what a proof of replication achieves. It proves that you're dedicating space to storing data.
Yeah.
Right? It doesn't actually matter what data, but what's important is that you're using the space and that you could be using the space to store any file that you would like.
Makes sense.
Okay? Proof of retrievability then verifies that you're storing a particular file. And a proof of data replication proves that you're storing multiple copies of the file.
Right.
So that's just a clarification of what these sort of different names for different kinds of proof of storage are.
Yeah, that's helpful.
Yeah. But to come back to your question, you asked...
how do we deal with the simple problem of having kind of a person impersonating multiple people?
Right. So the problem with a person impersonating multiple people and pretending to store multiple copies of a file but storing one is a case of somebody who is pretending to use less storage than they claim to.
Exactly.
To storing files.
Yeah.
Arbitrarily,
yeah.
right? If you wanted to guarantee that somebody is storing multiple copies of a file, then really the only way of doing that is to encrypt the file independently, say, 100 times, give them 100 encrypted copies of the file, and have them store that.
Yeah, I see.
There really is no way to force someone to store multiple copies of a file. The only thing that you can cryptographically guarantee is that somebody is using as much space as they claim to storing files.
Right, I see.
And so
They're
that's
using, like, say, n times the size of the file as much of storage.
I claim I claim to be storing the Lord of the Rings trilogy. We know the Lord of the Rings trilogy takes up 10 gigabytes of storage.
Yeah.
I have a 10 gigabyte disk, and I say I'm using my 10 gigabyte disk to storing this set of movies.
Yeah.
You can't, or let's say that I'm claiming that I'm storing 10 copies of that movie, okay? So I'm using 100 gigabytes of data.
Yes.
So you can't really verify that I'm storing 10 copies of this movie unless you specifically encrypt them, give them to me, and I can't really deal with them or understand what they are.
Yes.
But what you can verify is that I'm actually using 100 gigabytes to store the Lord of the Rings.
Yeah.
And what you can do is you can design this proof such that there's no economic incentive for me to use that storage for any other purpose. There's no cost or in terms of storage. There's no space savings that I could achieve by trying to fool you.
I see. And there's no way of encoding like other additional useful bits instead.
Exactly, right? And so if you take the perspective that nodes in a decentralized storage network are going to be, acting not necessarily maliciously, but rationally, and that if they could earn more dollars by saving a little bit of storage, and therefore destroying the redundant format of 10 copies of a movie, then they would take that action. And so you want to design a system where they
There's
can't.
just no incentive
There's
to
no
do
incentive to do that.
It won't.
Right?
It won't be at all more profitable.
Exactly.
At a very high level,
Yes.
in like maybe say the next 3 to 4 minutes.
Yeah.
How do proofs of replication work?
Great question. Proofs of replication take this concept called a proof of space, which is one of the flavors of a proof of storage. And it sort of combines it with the proof of retrievability, which we've been talking about. Remember, the goal of a proof of replication is to design a proof that I am using, say, 100 gigabytes of data or 100 gigabytes of disk storage in order to actually store data, and that if I claim I'm using this 100 gigabytes of data to storing a set of movies, then I don't have any incentive to not store those movies, right? That I can't really if I pass the protocol or I pass the proof, then you're convinced that I'm actually using all of my disk space.
Yeah.
And I can't really use some strategy of fooling you in order to save more than a negligible fraction of my disk space. And therefore, I might as well follow the honest protocol and actually use that space to store the movies. Okay, that's the goal. And so a proof of space is a concept in computer science that preceded proof of replication. And the goal of a proof of space was only to prove that you're using 100 gigabytes of disk to store arbitrary bytes of data. And proofs of space do exactly that. They store arbitrary bytes of data. They don't store interesting data. Actually, they store randomly generated bits, essentially. So it's not anything interesting. And so what proofs of replication do are they change the way proofs of space work so that instead of filling your drive with arbitrary junk data while producing this proof of space, you can fill it with really any file that you want. So you can fill it with useful data. And the rest of the protocol operates in a very similar way. You're responding to challenges, but the point is that the underlying thing that you're storing is not junk data, it's the data that you want to store. The tricky part of building a proof of replication was that, remember, there's this added constraint that we want to make sure there's really no incentive to cheat. Proof of space was used as a spam prevention mechanism or a Sybil resistance mechanism similar to proof of work. The goal was to make it, if you're passing a proof of space, then maybe you can save 10% of your data, or even 50% of your disk storage. You can pretend like you're using 100 gigabytes, but you're really only using 50 gigabytes. That's probably good enough for spam prevention. It makes it difficult. If you have some fancy algorithm that gives you an advantage, it's still difficult, right? The hope with a Sybil resistance mechanism then is that if somebody comes up with a fancy way of saving 50% of the storage, so will everybody. So everybody's still in competition. The problem with proof of replication, that's not good enough. You want this proof of space to be extraordinarily tight. What do I mean by tight? I mean that if you claim to be using 100 gigabytes of data or of disk space, you're actually using, 99% of that space, right? You're using as close to 100 gigabytes as possible. And that means that no matter what strategy you use, which would deviate from this honest protocol that actually stores the movies, you won't really be able to save much. And therefore, you won't really be able to earn much more. And the other penalties for failing to store the file that one might impose, in an ad hoc way, would be enough to just push you over the barrier to really behaving honestly, right? If there's some risk that you'll be caught, then you'll just behave honestly because the expected savings is too small. And so that's really what proof of replication is. It's a really tight proof of space that you can use to store useful data. And that's, without going into the techniques of how we really build that, which are covered in my latest series of papers, and I can talk a little bit about it at a high level, the most important thing to understand is the task is to design a really, really tight proof of space that you can use to store useful data.
What are some of the techniques then that people use or that you guys have pioneered to create these proofs of replication?
Good. Well, let me first say what the basic technique behind a proof of space is. So the basic technique behind a proof of space, I'm demonstrating to you that I am using 100 gigabytes of data, right? So I fill my disk with basically 100 gigabytes of data in a particular format, specially crafted for this proof.
Yeah.
And then I sort of compile that into like this small tag that I give to you. And then what you'll do is you'll repeatedly challenge me, okay? And the proof of space guarantees that I will only be able to respond to your challenges in a certain allotted time if I am still storing all the data that I initially committed to store. If I delete a fraction of the data that I initially committed to store, I will fail to respond to your challenge in the allotted time, okay? So one way of thinking about this, actually, and this is pretty close to the way it really works, is you literally ask me for pieces of the data that I'm storing. And the data is encoded in such a way that if I delete a small piece of the data, it has I'm deleting a small piece of that encoding, and so it has a tremendous dependency on the other pieces of the encoding, which were all derived from the original file format.
Yeah.
And it has this property that if I delete a small portion, then in order to rederive that individual portion, I'll basically have to redo almost all the work I did to encode the entire thing.
Yeah.
And that encoding process takes a long time. Now, within the realm of proofs of space, there's two senses of time. There's the total computational effort that I put into generating this file format. And then there's also wall clock time, or like how long it takes to actually do it, even if I threw a massive parallel effort at doing this.
Yes.
And the strongest type of proof of space would guarantee that if you gave me 5 minutes to respond to this challenge, I would not be able to rederive my entire encoding in 5 minutes, no matter how much parallel effort I threw at it.
Right.
And that's the sense of security that my latest work in proof of replication achieves. And the way that proof of replication extends proof of space is not just in the way that one generates the encoding, so that it's not just an encoding of random bits, but it's actually an encoding of a file that can be decoded.
Yes.
Right? You might be interested then in asking about the decoding step. So when you talk about proof of replication as opposed to proof of space, now it's not just important how long it took you to derive this encoding of the data, right? It's also important that you can decode the data and recover the initial seed that you used to generate.
Of course.
The data.
The seed being the file.
The seed, in this case, being the file. And then you also might be interested in how long it takes you to decode the file. If I have to take as long to decode the movie as it does to encode it, which is by design a long time, right, for a security to hold, then that might not be so desirable for a decentralized storage network. So proof of replication designs this encoding process in an asymmetric way so that it takes a long time to derive a encoding of a file,
in a very short period of time.
But a very short period of time to recover it, or at least the decoding step could be parallelized.
Yeah, that's awesome. And so to summarize, so what you do is you encode the file in such a way that if you give the file over to someone who's going to store it, and presumably that person may decide to try to cheat by deleting certain portions of the file.
That's
and they
right.
could do that because they could always rederive those parts from the other parts, but that'll cost them some amount of computation to doing that. And so the key in proofs of replication is that you encode the file in such a way that the dependencies between all of the pieces of the file are such that deleting any one piece will cause for a lot of the encoding to have to be redone to such a degree that the amount of time that would take would put them beyond the timeout phase that the challenge demands.
That's
so
right.
they would sort of fail to meet the challenge in time, and then you would know they don't have the entire file. Huh?
You can think of it, if you're familiar with error correcting codes, then you can think of it in a similar way, where the goal of an error-correcting code is to encode an original file format such that if you lose some of the pieces of the file, you can recover the whole file.
Right.
The goal in proof of replication is if you encode this file in such a way that if you lose a few pieces of the file, it takes you a really, really long time to rederive the pieces of the encoding.
Yes, of course.
Right? And therefore, if your challenges those pieces, you won't be able to respond correctly on those pieces within the allotted time.
Makes sense. Switching gears slightly, there's this sort of a frequent question that arises in the world of crypto, which is, what are the implications of using a useful resource or a commoditized resource, something like storage, for the security of a network? The critique often is that if the thing that is securing the network is something that is highly commoditized, then anyone who owns a lot of it could presumably just use it to attack the network, because the security of the network is sort of based on kind of like the use of this resource for security. So if I say I am Amazon and I have an enormous amount of storage available that I could choose to just sort of deploy to attack the decentralized storage network, then I could presumably do that. Whereas in a world where the resource is not really commoditized and actually depends on sort of special made hardware for that particular blockchain, in the case of Bitcoin, for example, that's much more difficult because no one other than people who are already mining Bitcoin, presumably, have access to that hardware. And so as a result, the security for that kind of network might be higher. What are your thoughts about this kind of debate?
It's a difficult question, right, Ali? If you make it such that the barriers to entry are really specialized, then you also make it difficult for just anyone to participate, right? Like the goal of a decentralized storage network was, oh, you have some extra space on your phone. Maybe you can participate and use some of that extra storage without doing anything else to contribute to the network. But then you bring up an excellent point, which is that if there's economic incentives involved, then maybe we do want to make it so that you have to invest in special, hardware, so that someone who has a lot of extra storage, or just has a lot of storage that they're using to run a business like Amazon, can't just pick up their, what they're using for their everyday business or their everyday use, in your case, which is your phone, and use it to attack this network. I don't know that I have, an excellent answer to that question, because you want to achieve some balance between those two extremes. I would say that when you do something like proof of replication, it's an extremely inconvenient way of storing files, right? So if Amazon were to convert all of its storage to proof of replication formatted storage, it would be quite inconvenient, if not costly, actually. And so, to some degree, right, you want to design a system where there are specialized efforts that people need to go through in order to participate. And you want to design a decentralized system where you don't want the massive cloud centers who are already storing a lot of data to find it really easy to convert all that data to a new format that's equally convenient. But what you would do is you want to encourage participation, so the costs aren't exceedingly high of participating. You don't have to buy specialized, formatted hardware or an ASIC, but you need to do this extra inconvenient thing in order to participate in this network. But because you're just someone with some extra storage on your device, and you're not trying to compete with Amazon, that you're willing to go through that step in order to participate. So I think that's sort of where proof of replication falls. Somewhere in between something which has high, barriers of entry, such as something which requires ASICs, versus something that is just so convenient for Amazon to do and participate in. Without, somehow compromising the rest of their operations. Although, of course, I would, leave with the caveat that it may be the case that people would be able to design ASICs which would be better at proof of replication. It's really hard to prevent that.
Yeah.
And so I can't say that designing an ASIC to achieve a small savings with proof of replication would be impossible. We can say that since proof of replications are really tight proofs of space, that we know that you have to use, say, 99% of the space. But remember, there's still some computational cost, and you can optimize that. And so it's hard to say whether it's completely ASIC resistant.
Yes.
It's easy to get carried away and say that, oh, proof of replication, well, it's inconvenient for Amazon to do this, so there is some barrier to entry, but it doesn't require ASIC, so anybody can participate.
Yeah.
It's all of these can be challenged, right? Amazon could, if they really, really were incentivized to take down a decentralized storage network that was running a Bitcoin-like system where the proof of work was now proof of replication.
Right. Which is what we're talking about.
Which is what we're talking about, right?
And they could potentially double spend, or they could.
They could do it, right? And then you have to consider what would be the cost to their current operations, right? Mm-hmm. What would be the storage overhead or the computational burden of, or remember, proof of replication encodes files in a certain format, but it's still not the easiest to extract the data from that format.
Exactly. It's not nearly as useful as just like the plain format where you just have the data.
Right. I mean, when you're talking about a huge business like Amazon, where the potential impact of making a small difference in the latency that they have for their customers, or a small overhead in the storage that they're using, it could really be detrimental to the business. Whereas if you just have unused storage on your phone, and you're willing to use all the rest of the storage that you have on your phone and fill it up to capacity and participate in something that you just wouldn't be able to participate in anyways, then it starts to make a little bit more sense. Then maybe it doesn't matter that proof of replication requires you to use 1% overhead in the storage, but to Amazon that matters a tremendous amount.
Yep.
And I think that's another way of thinking about this inconvenience factor, which proof of replication has, and may actually be beneficial to the system.
Yeah.
I don't know if it's beneficial when if you're asking whether decentralized storage networks will have lower costs than Amazon. Boy, that's a really hard question.
That's a hard question.
Yeah.
Certainly.
Who knows?
Oh, yeah, you're right. These are hairy questions. I think in the end, the calculus there would come down to how much could an entity like Amazon, not necessarily Amazon, profit from sort of accumulating so much storage that they can overwhelm the security of the network and then double spend and actually interfere with consensus of the network. And I think you are correct in that it's kind of like a hard problem to reason about because we don't really know what the numbers lie.
Yeah, so. I would like to think of it in some sense, and this may be an inappropriate analogy, but the farmer's market of file storage. It's pretty inconvenient for one of the main food distributors in the U.S., like let's say U.S. Foods or Cisco, to bring food to a farmer's market, right? But farmer's market allow farmers or individuals to just contribute, to the local food produce economy, and the inconvenience of setting up a booth and bringing a small amount of vegetables, say a long distance, to bring it to a local city to participate in a farmer's market, is not a perfect analogy, but somewhat of an analogy to using proof of replication, which is not optimized for efficiency, but it is appropriate for the participation of just individuals who want to contribute storage to a decentralized storage network that is not something like Amazon.
For sure.
Yeah.
Awesome. Well, to wrap up, give us a teaser of how this is connected, sort of your work with proofs of replication, to some of your more recent work on accumulators.
Yeah. So it's interesting. There is somewhat of a connection. We've been talking about incentivizing distributed file storage. And we even mentioned, Bitcoin as an example of a decentralized file storage network, in the sense that all the miners in Bitcoin are contributing to storing the ledger of Bitcoin.
Yeah.
And in other blockchain systems, all the validators in the network are participating in storing the state of the accounting system and verifying transactions. So you could also wonder whether proof of replication would be useful for incentivizing people to actually participate in storing the database of financial transactions, which could grow quite large. But then there's another question, which is, well, what about just reducing the storage burden in the first place, so that you don't require tremendous incentives for a node to participate in in consensus, or to participate in the collective and distributed maintenance of an accounting system like Bitcoin.
Yeah.
And that's what accumulators are about. They're about, if everybody stores just a few transactions in the network, okay, then how do other nodes in the network verify that when I submit a transaction, that my transaction references my account correctly, without having to store the entire list of all accounts?
Yep.
Okay. And we can talk about that another time.
Absolutely,
but
sounds fascinating.
it's all about how do you basically remove the requirement that everybody in the network needs to store the entire Bitcoin ledger, entire ledger of accounts, in order to participate in validating that transactions are correct.
Yeah. Well, we'll leave it with a really compelling teaser that you gave me earlier, which is this is a way by which you can separate consensus from storage.
Yeah, I recently gave a talk on this, and a way of looking at this is a separation of consensus and state. But really, it's a separation of the consensus layer of a blockchain accounting system from the storage layer, where you don't have to have the same nodes participating in both. You could have a whole bunch of cell phones running the governance of and validation of transactions to the network, and then have some heavy servers actually storing the actual storage of the network in an optimized, decentralized way. Optimized for storage, but not necessarily participating in consensus. So
fascinating.
Yeah.
To be continued.
To be continued.
Thanks for coming along.
Great. It's great to see you.
Good to see you.